Heavy topics this morning. Okay, so this is gonna be fun. There's a lot of slides. I'll make sure that you know the stuff that I want you to retain. Okay, but there's a lot of show and tell in this presentation. Okay, so yes, we could collect a UVVis spectrum like you were talking about in your little article. We could pick the peak maximum. Oh boy, we've done that. Okay. We could assign it maybe to an N to pi star transition or pi to pi star or something like that. Okay. But even better, we could use Gaussian to calculate the spectrum and the UVVis. And it's not taught that often. It's using the Gaussian to calculate the UVVis spectrum to know what's going on under this. But here's the beautiful thing. Everybody look at this one. Okay. Everybody look up. Daye. Look up. Look at this. No more people. You can't see it. Oh, I built the whole thing up for this great thing. Yeah. Oh my God. Okay, so here's the deal. We went through this, peak the maximum, you assign the pi star, right? Or you could do the Gaussian to calculate the UVVis and for the rest of the course. All right, we're done with the peak picking. Yes. So yeah, so I'm so excited. So is Oprah. It's like no more. What? Looking at the noise. Is that a peak? Yeah, I think it is. Yes. It's on the line. Yeah. All right, good. Well, y'all are warming my heart. That's right. I don't know if you're lying or not, but you're warming my heart. It doesn't look like you're lying. Okay. So yeah, that's right. So we're going to use the Gaussian software to simulate UV-Vis spectra today. And so you build your molecule. We've already built some molecules and so on. But here we have a new thing. So on the job type tab, so in your notes, I don't have the little bullet that says job type. So you might want to add that in. I added it this morning because I was looking at my notes yesterday. I was like, there's something missing. Yeah, so on the job type tab, that's this first tab, you don't pick opt freq like we're used to. So on this one, we used to put opt freq for vibrational stuff, the frequency calculation. Okay, we optimize first and do the frequency calculation. Now, okay, when you do your molecule the very first time, you want to optimize it. Okay, so go ahead and optimize your molecule. So we do that one job, but then once we're done with that job, we bring that output back in as a log file, and then we go to this, and we go to the job type tab, and we pick energy. Okay, so we just pick energy, and then we go to the method tab, and we do Zendo. Now you could do some of these others too. CI is configuration interaction, and so it moves the electrons around into the different orbitals, different configurations, and looks at the total energy of the molecule. And I don't exactly know how it does it, but it lowers it finds the geometry and the lowest energy of the molecule, not the geometry, the lowest energy of the electron cloud by looking at the interaction of different electron configurations. Mathematically, no idea how that works. Then we have the time-dependent SCF. TD is time dependency. And when we add in that TD SCF, then we can get density functional theory methods and so on. But Zendo's the fastest. Okay. Z stands for it's a guy's name, Zerner, and this INDO is the intermediate neglect of differential overlap. And so, do y'all in your undergrad, did y'all ever do Huckel theory? Yeah, advanced integrated. You have the adjacent atoms that overlap their orbitals and so on, but then you have atoms that are too far away. They have the overlap of zero. Okay, and so that's what we're talking about, the overlap of atomic wave functions, and we're just doing adjacent atoms and so on. It's kind of like Huckel theory. That's what that's what INDO stands for. The Z is the Zerner method, and so then if we pick that, then it's going to allow us to get the transition. So it'll produce output in the output file, the wavelength and the oscillator strength, which is essentially that transition dipole moment integral. You know, we calculated that with the particle in a box. And the Gaussian's calculating it now in 3 dimensions for electronic transitions. Okay. So with this, when the calculation is over, we could simulate the spectra, which is what we're going to do today. We're going to look at molecular orbitals, electron density surfaces, which sort of shows the electron cloud, and the potential energy surface map, or electrostatic potential map. Now, we covered this a little bit earlier in the course, but I don't remember how far I took you guys, because I teach this also at the undergraduate level, and I don't remember what we did. What did we do with surfaces this semester?
I think you only brought them up last time, was what I remember.
I just showed them, but y'all didn't calculate any of them? Okay, so I would like to add that to the project. So this last project, I'd like for you to do a couple of these surfaces, like show an MO, show a density surface, and make an electrostatic potential map. Because those are really essential skills, okay, in using Gaussian. And what we call post-calculation options is to show these kinds of things. And you'll learn how today in the notes. So let's look at the molecular orbital surfaces. So I added a little supplemental to the notes on Blackboard, and it has these 4 slides here. So the molecular orbitals are captured in the checkpoint file. And so you have a .log file, which is the text output. Okay. And then the checkpoint file is not clear text, it's a binary file. And it contains all of the data of the electron cloud in it. And so if you load the checkpoint file, then you can go to the Tools menu and click MOs, and then you get this window. So this thing generates this window right here. And then once you have that window open, you can go down here to the Visualize tab. You see number 3 here, Visualize. And then you have this list here, this add list, or you could type this, the molecular orbitals in this list, or you could come over here with the mouse and you could click them. And if you click them with the mouse, they highlight. And so you can highlight them, the ones you want. Right now, what do I have highlighted? Can y'all tell me? Like if you were to look at this diagram, we have names for the 2 that are highlighted. Yeah, all right, good. I didn't know what to expect. This is the highest occupied molecular orbital, and this is, yeah, that's right. That and electronegativity, I'll use it to explain everything in general. Students love that. I don't know why. So this is the highest occupied. You see occupied. Here's the occupied electrons. Okay, highest occupied molecular orbital and lowest unoccupied molecular orbital. So we click those 2, and then it says here highlighted. 5 is highlighted, and if you click this drop-down box, you could do all. You could do highlighted. You could do occupied or whatever. There's some options, and I just picked highlighted because it's faster. And then hit update, and so it does it like there's a back end, and it goes out and it does this back end calculation to calculate these MO surfaces. And so then once you've done that, then you get the picture. You can copy that MO image and paste it into PowerPoint. And then I wanted to show you this. This is a slide that's not in that supplemental. But if you click on a picture, you have this picture format ribbon. If you click that over here under color, you can click color and then come down here and say set the transparent color. So this guy right here, if you click that, then it's like a little eyedropper tool, like you're going to suck up some paint or something like that. And if you go to your image and you click the blue region of your image, it will make that blue region transparent. And it'll disappear. So then you can put your MOs on top of, text or whatever, and it's not just this big blue box.
I don't think this.
It's not in the supplemental. I added it this morning because I thought, well, I want to show them the transparency thing. So this idea, where is the transparency tool? It's on the picture ribbon. So once you select a picture, this ribbon shows up, and then you come over to color. Okay, there's a thing that says transparency, but that's the whole image. You can make the whole image 50% transparent or whatever, but what you want to do is pick a color to make that color transparent. So you go to the color box, you click on that, and then you click transparent color, and then you go up and you select the blue region, and it all disappears. Very nice. Okay, so these are the pictures that you get without the. Oh, I didn't do the transparency on these, but what'd you say?
Oh, I was just gonna say, I tried to change the colors of these before because it just really hurts my head seeing the red and the green. I can't stand
Oh
it.
yeah.
And I didn't work.
I don't
on
know
it, so
how you can change the green and the red. That's just what Gaussian does. So those colors grate you, huh? Well, just I don't know. It's Christmas to me. Think of Christmas. The holly and the ivy. That's right. So we've got red and green, and so we'll just call it Christmas colors. Yeah, I don't know why they picked that. But you could also right-click that blue region and go to View and Display Format. And y'all did this with the vibrations when you wanted to show the dipole derivative and the Cartesian coordinates. You right-clicked, you went down to View and did Display Format. But you could also go over here to the Surfaces tab. So on the Surface tab, you can play with this format. And so this is the solid one. Here's the transparent. You see, isn't that nice? You can see the atoms inside. Yeah, and then here's the mesh, which is nasty, but some people like the mesh. I don't know. It's not my favorite, but this is the like the wire mesh that you can see through. Yeah, and so that's different view settings. What's that? That the mesh, yeah, it's like a cage, yeah. And you can play with the Z clip too. This down here at the bottom, you can play with that to see what it does to the image. So these are the molecular orbitals. These are the kinds of things that come out. Now, sometimes you can use the terms of pi and pi star, right? Like in this case, this is clearly a pi bond, even though it has some funny business over here on this ammonia, on this amine. It's clearly a pi bond, and this is clearly a pi star. You see that the node breaks the bond, and so that would be anti-bonding for those two carbons. So even though we are in molecular orbital theory, and this morning I just disproved it, and then we did that in this class too, local bond versus molecular orbital theory, how the X-ray photoelectron spectroscopy really shows that molecular orbital theory is the theory that we need to use for the electronic structure of a molecule. Okay, and the idea of sigma bonding and pi bonding is really kind of lost on us because is this a sigma or a pi bond? I mean, what about this up here? What would you label that bond with? So the labels of sigma and pi don't work really well for anything other than a diatomic. And the only reason it's working well here is because we have two atoms that are being bonded in a pi manner or a pi star manner, but in terms of the whole molecule, it's hard to say what is a sigma and what is a pi. Now you can still, if you have a pi, if you have a pi framework like this, I can't really see this molecule from the side, but you might have like a pi framework where it is like pi character, side-on character of p orbitals through the whole molecule, and so you would say it is a pi system. And if it's the sigma framework, everything will be containing the plane of the molecule, and that would be sigma, like a framework of sigma bonds, but it wouldn't be a single sigma bond. Any questions on the molecular orbitals before we shift gears? So we get those from this molecular orbital tool right here. And so you have to load the checkpoint file, and then you go in and you select your orbitals that you want to pick, say generate the highlighted ones and hit update, and it'll make a list. And then you get little check boxes over here and you check the one you want to see. So then, yes. Yes? It's a little different than, what's your question? Oh, yeah, good question. You really can't say much about it at all. I mean, this is just a picture of the molecular orbital. And so in molecular orbital theory, we really can't say, you have to get out of your mind that there's two electrons associated with a single bond. Like a carbon-hydrogen bond does not have a carbon, a hydrogen, and two electrons holding those two together. Those two electrons are on a molecular orbital that goes over the whole molecule. And so you could say in this particular case, this is a bonding for these carbons. Bonding. Here, bonding here, and on the other end is an amine group here too, so, and bonding here. But it's not bonding here. It's weak. It's weakening this bond, it's weakening that bond, and weakening that bond. So it's antibonding for those bonds. So we can't classify this molecular orbital as bonding or antibonding because it's not an or situation. We have to talk about particular regions of the molecule that are strengthened or weakened by that. Yeah. So it's a different mindset. Okay. Yeah.
Bonding or
Yeah.
different places.
Yeah.
Like that right there at the bottom where it's all.
Yes. Well, yeah, and the very lowest would just be a big blob with no nodes anywhere. hmm And that's always the lowest energy because think of the slinky. It's the whole thing's moving up and down. There's no nodes anywhere, and that's the lowest energy one. And this, the whole cloud is expanding and contracting in all directions. There's no nodes, so that's the lowest energy. Energy is related to the curvature of the wave function. And these guys, the more times they go through zero, the more curvy they are. So it's curving up, curving down, curving up, curving down as it goes across the molecule. And so that's a very curvy wave function, and so that's going to be higher in energy. So let's look at some of the other surfaces. This is contours, surfaces, contours, and maps option too. So you load a checkpoint file, and then you go to results, and under results, you'll see surfaces and contours, and it'll open up this box right here. So that'll give us this box right here. Now, this has a couple of MOs in it already because I calculated them already, okay? But a lot of times there's nothing here. If you haven't calculated any MOs, then it won't have anything inside. And so you come in here to the cube action, and it says new cube. You can say new cube and then pick a density surface. So here, generate cubes. So if you click new cube, you can put type like total density and hit OK. And this is what you get. So you'll get the total density. It'll show up down here in the surfaces area, and it'll tell you which surface is being shown. And you can see electron density from the total SCF. SCF is self-consistent field. That's what Gaussian used to find the energies of all the individual wave functions. So it would change the coefficients of the wave functions, like the mixture of a 2p and a 2s and a 1s. All those mixtures, it changes them slightly until it comes up with what's called a self-consistent field. Basically, the changes that would make it better are so small that it can say, I'm done. Okay, so then it's showing that density, and here we could right-click on it, we could go to surface, and we could make it transparent, we could make it a mesh, we could use the Z-clip and like clip the front of that surface off, and then we could see the atoms inside. But that's the total electron density surface. And you can kind of see that even though there's, we don't draw the lone pair of electrons, and there should be electron density here, and the cloud is pretty big right here. So even though local bond theory is not technically correct, we see that region on the backside of that nitrogen has a lot of electron density on it. We're not going to assign 2 electrons to it. That's just where the MOs show up, but we have those p orbitals on that nitrogen. Some are being used for bonding to the hydrogens, but then there's some that are not. And then we could go into that generate cubes, and we could type in ESP for electrostatic potential. So potential, it's going to be the like electrical potential. And so if we walked around the whole molecule carrying a positive charge, so here's my little guy, he's walking along carrying a positive charge. Okay, and he's measuring the force on that positive charge. So if he's over a positive area of the molecule, it's going to be pushing away. And if he's on a negative part of the molecule, it's going to be pulling towards the molecule all along that density surface. Then that would be the electrostatic potential. And then we can map that onto this surface and add colors. And so here's the electrostatic potential map on the density surface. Now the old set of notes had previous version of Gauss view. And so this is the modern version of Gauss view, and I went ahead and updated the notes last night. That's why I was doing that. And I had a hard time getting this picture because by default was putting the electrostatic potential on MO number 9. I didn't want that, and I don't even know why that would be a thing that you would want to do. It's just that's what it was generating for me, and it was giving me a headache. It's like, why is this not working? It's important to make sure that you click this first. So you click the density surface. So this is your pro tip. So in the future, when you're calculating your electrostatic potentials map, you want to make sure that the density is selected before you go to surfaces and say select. You do this, then do new mapped surface. So when you click surface actions, you can select new map. It'll ask you what kind. You say electrostatic potential, and it'll map it onto whatever's selected up here. And so then that's what you get. And here I've used that Z clip to kind of take off the front of this surface so you can see the atoms inside. I had to play with these levels. It was pretty much all red. And so notice this, everything's negative. I don't know why everything's negative, but it is. It goes from minus 2.5 to minus 1. And there's a little bit of a hint of blue right here next to that hydrogen. And then it's red kind of in the middle. So this region right here is negative, and this little tip right here on this hydrogen is positive. And that makes sense. This molecule would hydrogen bond. It's an NH2 group. It should hydrogen bond. It's not very positive. It's really just less negative. But still, that's what we have in this molecule. So that's an electrostatic potential map, ESP, on a density surface. Here's one that's even better. This is benzoic acid. And so naturally you see the negative oxygens and the positive hydrogen. Look how blue that one is. And it's actually positive. This is plus 0.21 is the deepest blue, and this is minus 0.21 charge units where the deepest red is. And so this whole map is then mapped out between those two endpoints. So that's a pretty handy tool. You can see that this is an acidic proton by looking at the electron cloud, because that's a positive portion of the molecule. So in water, what's going to happen is the oxygen is going to be attracted to that part of the molecule, and we call it a hydrogen bond. So the oxygen nestles up to that, and that's a hydrogen bond, really strong association. And in fact, it could steal the hydrogen, and we have, deprotonation. So chemistry can be understood from the electron cloud, and that's really the best way to do chemistry. So here's this molecule. It's nitroaniline. So aniline is a benzene amine, and then you put a nitro group on there. You can put it in 3 unique places: ortho, meta, and para nitroaniline. Now this one is not a map that I'm going to have you guys do, because even I've had trouble getting this map out of the modern Gauss view. I did this years ago with an earlier version of Gaussian. But I wanted to try something here. I've got the electron surface. I'll just draw a surface here. And I've got a surface here. And if we were to look at them, they're not identical. So notice it's gotten the electron density's gotten a little bigger in this region. Okay. And so we're gonna call that positive change. So we're looking at a difference map. So how did the electron density change? And then it got smaller over here. So that's a negative change. You'll see in a minute why I want to do this. Because in a UVVis spectrum, we have, an occupied orbital here, an unoccupied orbital there. We've got a transition. What's happened to the electron cloud? Now you might say, let's just look at the molecular orbitals and see which molecular orbitals are connected by this transition. Because that's the way I think about it. You got an occupied molecular orbital, an unoccupied molecular orbital, light comes in and electron hops. I wish it were that easy. Okay. This is a research project that I did on these explosives. This is triamino trinitrobenzene, and it's a yellow explosive. And if you shine light on it, it turns green. Okay, and so it's a photodegradation process. And at the time, nobody knew what was happening, what was changing in the molecule. They had done sensitivity studies. It was an explosive. They didn't want it to become more sensitive because that would be dangerous, right? You set this explosive in the sunlight, you make it, and it's safe. You can hit it with a hammer and it won't go off. Okay, you put it in the sun or in a room with fluorescent lights, it turns green. Now you pick it up and it drags across the table and it blows up, kills people. Yeah, that's the fear. That's not what happens, but that's the fear, right? We have this green explosive. Is it going to kill somebody? Right? And so they did the test. It doesn't get more sensitive, but what is happening? So this is the research project that I did for Pantex. And so, yes, we could assign things to N to pi star and pi to pi star, but we said those are very difficult to nail down in a bigger molecule. So let's look at the UVVis. And so these are limited in these kinds of definitions of N to pi star and pi to pi star. So let's look at these energy electron density difference maps. So here's our molecules, and they weren't going to let me bring triamino trinitrobenzene to Sam Houston State. It's an explosive, and you got to be 21 to work with it, even if you have all the permits, So even then, I had to card people at the door of my lab. So I use these nitroaniline as stand-ins, as analogs. And here's the UVVis spectrum of 3-nitroaniline. So here it is in hexane, here it is in water. Now we could use that in determining some of these designations of pi to pi star, N to pi star, and so on. Some are more affected by protic solvents than others. But we look at the Zendo calculation and it's not that bad. So this is one of the take-home lessons here. So look at the water spectrum and look at this Zendo. I mean, this is a pretty good correlation of peaks here. Or at least I think it is. We've got 3 major peaks in both the experimental spectrum and in the Zendo calculation. So that's really great. These are the results that come out of Zendo. You get a wavelength and an oscillator strength. This is that transition dipole moment integral. X, Y, or Z squared. Okay, so that's the oscillator strength calculation. I'll say psi and psi prime, so lower and upper. And then this is the wavelength of the transition. And then here's the 4-nitroaniline. Also matches pretty well. We got a really strong peak. It's still in the UVVis, but it's a strong peak. I mean, it's still in the UV. It's not quite in the visible. And so here's the results. So if we look at these wavelengths, let's take this transition, this 325, really strong transition, and see what kind of molecular orbitals are associated with that, right? It seems straightforward that there would be a molecular orbital here and there, and that this wavelength of light is causing this to jump from one to the other. Those pesky electrons are really fast, and you have interactions of multiple wave functions in the lower state and multiple wave functions in the upper state, and it's really frustrating. So this transition here has 10% of this transition, 67% of this transition, and I guess to interpret this, out of phase 10%, I don't know. These are the coefficients of these mixtures of molecular orbitals. So you have 25 going to 28. So this is 25 here. This is 26. This is 27. This is 28. So we have a little bit of this one. And 26 to 27, we've got a little bit of this one. And then 26 to 28, we've got a little bit of this one. All for the 347 peak. That's a mess. And so I was very disappointed when I got to this point to try to interpret the UVVis spectra, because we have mixtures of all of these MOs that give us the peaks. It's not as clean as a vibrational transition, 0 to 1, a fundamental, right? Or HOMO to LUMO. The HOMO to LUMO would be the 26 to 27. And it's present in this one, and it's the most abundant. Okay, it has the highest coefficient right here. So you could say that that's the HOMO to LUMO transition. But I just don't understand, even I don't even understand the mixture in of the 25 and the 28 and what role that's playing in that transition. Is it changing the intensity? Is it changing the frequency a little bit? Yeah, so this is not easy to interpret in my understanding. And I'm sure you would agree, because like which one is it? We got 3 different transitions listed. But you could go with the largest one, and that is the HOMO to LUMO, which would be the longest wavelength transition. So great. But then it gets even more complicated. Look at this one. This is the biggest mess ever. Yeah. So here's the biggest one, 26 to 28. And so that's this one here. Yeah. So it's complicated is the take-home lesson. So it can model the UVVis, but assigning it to individual pairs of MOs is not always easy. Okay, so these combinations of MOs are confusing and complex and don't clearly explain anything. All right. So let's do electron densities. Let's just back out of the individual wave functions and look at the whole cloud, the electron cloud, and see if it changes. Because again, if I think of the particle in a box, you've got the oscillating, the ground state, just the slinky, right? No nodes. And then I go to the first excited state, and all of a sudden it's doing this. Well, what if you square that wave function? I've got 2 places where the electron, so it was in one place in the middle, and if I square it, and if I excite it to the first excited state, now it's moved, it's sort of split. It was primarily in the middle, and now it's split into 2 places. If I were to take the difference between those 2 states squared, then I would see a movement from the inside to the outside. I'd have negative numbers in the middle and positive numbers out here. And so we would see a red spot in the middle where the electrons left, and a blue spot where they went to. And so that's what we're doing here. We're calculating these differences in the density of the ground state and the density of all the different excited states that we hit. So with this wavelength transition, we get a difference map. So let's just learn by looking at the pictures, okay? So here's the difference map, electron density difference map for this transition. And you can see that this is now easily explainable. Electrons have left the ring where it's red and went to the functional group, the nitro group. So this is kind of like a ring to nitro transition of electron density, and I don't have to worry about which MO was involved. I just know that light came in, hit the molecule, and electron density went out to the nitro group. Okay, that makes that nitro group more reactive. And so we could tune chemistry this way. If we hit it with 340 nanometer light, we would be activating that nitro group. And that's pretty nice. Like we could really maybe use this to model or to push our molecules around in certain ways. This one is more ring to nitro group, another ring to nitro group. This one is not quite, this just looks more like ring to ring. So maybe it's a certain orbital on the benzene ring going to another orbital on the benzene ring. We don't see a lot of positive here. There's maybe slightly blue here. And then here's one that's clear. This is all on the nitro only. So it's going from the oxygens into the nitrogen. It's moving in that direction. And then here's some more. This is going from the, outer parts of the ring sort of in line. So that's kind of like this is gaining, and then the red is losing. So it's going from outer, so that's again a ring mode, but also delocalized onto that nitrogen bond. And here another ring mode. So most of these we can conclude are ring transitions. One is like ring to nitro group, and then this is completely within the nitro group. And so that would help you track. Let's say you put this in another chemical environment, and let's now go to the para. So here we have ring to nitro. Here we have some small ring to nitro, and then here's that nitro one. It kind of stayed put, even though we went from meta to para. Okay. It was around, let's see what it was. This is about 220, it looks like. And this one's about 220. So it looks like it stayed the same spot. So these are electron density difference maps. And I think they're useful. They're pretty hard to generate though with the new version of the software. So if you figure that out, I'm not going to ask you to do this, but if it's something that you just get excited about, maybe you can figure it out. And if you figure it out, reteach me. I knew how to do this with like 2 versions ago, and so I'm having trouble with the Gauss V6. So let's apply it to TATB. So here's TATB, and here's all of the different proposed things that it might have happened. We might lose a nitro group. We might lose just an NO and have just an oxygen radical on there. We know that the final product is got an unpaired electron because it's it is measurable with the electron paramagnetic resonance machine. And so then we might have lost a nitro with a hydrogen. We might have just lost an oxygen and have a nitroso group. We could have lost an amine. We could have lost water and made this furazan ring. We could lose a hydrogen maybe. Maybe we could gain a hydrogen. So there's all these different possible routes, and I went through a bunch of them. Here's the UVVis of the TATB. This is the yellow substance, and the Zendo simulation does pretty well. Yeah, it is shifted, but still it has the same profile. So that's fantastic. And here's the electron density difference map. There is a peak over here on the far right that you just can't see because it's so small. And again, it's those nitro groups going into the ring and into the nitro groups. So that would be like an N, maybe non-bonding on the nitros to pi stars on the nitros and into the ring. But it's all 3 nitros. It's not this non-bonding electron on this particular nitro group. Here's some ring modes, ring going out to the nitro groups. Here's another one, that's degenerate mode. And here's another one, ring going out to the nitro groups. There's a couple of those. And then here's just oscillations across the whole molecule within the ring and their functional groups and so on. So now let's look at the one with the nitro loss. It does kind of match these major features, I would say here. So that's encouraging. There's not a lot of peaks here in the experimental, but there is this little hint of a peak right here. We struggle with this UVVis spectrum of the green TATB because it's not soluble in anything. I had to dissolve it in concentrated sulfuric acid. Well, did I get the molecule or did I destroy the molecule? That's a harsh solvent, okay? But it went right into sulfuric acid and I got the same spectrum for the yellow. And so I was like, well, the yellow survived, and the green, I still have this major peak for the green, so it seems like the green survived, but I got a new peak here at 600 in the green. And so there's a peak out here too. So there's again a nitro group there. And then look what happens here. This is definitely that missing nitro group, the lone electron. We've got some modes that are associated with that. So I went through and basically, assigned all these peaks using the electron density difference maps. So the conclusions are Zendo is really inexpensive computationally. What was the longest calculation y'all had for the frequency calculation or optimization? How long did your calculations go for your opt freaks on your project molecules?
What's that called?
30 seconds.
30 seconds?
Yeah.
They were small molecules, but they were B3YYP, right?
Like,
Did you have a silicon? No? What did you have? You had a what?
state.
Oh, yeah,
So
yeah.
when I was trying to model the.
Yeah, and the acetate's got a dihedral angle, and so it's going to be twisting around there until it finds the minimum. And that's probably, it was the optimization. If you look at it, that probably was the long one. 30 seconds?
I ran it did it in 30.
And you did B3OIP.
I just thought it wasn't,
Wasn't really long, huh?
it's not a little mean.
Yeah, these take 6 or 7 seconds, like not long at all. Yeah, so these are definitely while you wait calculations. The Zendo for sure. Now the TD, time dependent DFT, that's just like a B3OIP calculation. It can take quite a long time. Okay. And so what we'll do is I'm going to produce a video for the specifics on how then you take that Gaussian output and turn it into a spectrum. And then we're going to get into modeling the color. So what we really want to know, not so much on TATB, not so much just assigning the peak to electron density difference map, but what color is this molecule? Can I take off an amine or a nitro or whatever and figure out which one of those is green? And so since we can model the UVVis spectrum, maybe we can also model the color. And so that's what we're going to talk about next. So we'll get into the colorimetry calculation next time.
Yeah, we should